but it's this kind of frozen place with strange eruptions from the surface that kind of rise up into space but then go flat.
For ages, people have been both fascinated and perplexed by the idea of time. We frequently take it for granted, but it is a fundamental feature of the cosmos that we encounter on a regular basis. Time permeates every aspect of our lives, from the ticking of a clock to the changing of the seasons. However, what exactly is time, and what do we actually understand about it? What would happen if you traveled back in time? All of these questions have been addressed by renowned British scientist Brian Cox. Come along with us today as we explore the mysteries of time and the consequences of traveling back in time. According to Einstein's theory, traveling back in time is actually impossible due to the speed of light in four-dimensional space. Although you can envision wormholes and similar concepts that allow you to tunnel through and take shortcuts, it fits into the geometry in that fashion. The chronology protection conjecture is a theory put out by Stephen Hawking. According to the conjecture, it appears to be illogical from a physics standpoint. It isn't a method of creating a world that would enable you to go back in time and stop your parents from meeting before you were born, or anything similar. It is therefore a hypothesis that time travel into the past will always be prohibited by the laws of nature. Now that's only a hunch right now. It may or may not be true in Einstein's general theory of relativity, but it is unquestionably true in his so-called special theory. However, the majority of theoretical physicists would say, "We think, we'll conjecture, physics protects the past." We're not sure because you can have these shortcut things. Time is a measurement at its most fundamental level. It enables us to quantify the time between events, sequence them, and determine what occurs before and after. The evolution of human civilization has depended heavily on this comprehension of time. Time is a tool that we use to plan, organize, and make sense of the world. Although measuring time appears to be simple, time itself is much more complicated. For thousands of years, people have been aware of how time is perceived. In order to calculate days, months, and years, ancient societies monitored the motion of the sun and stars. They employed a variety of tools, like as water clocks and sundials, to measure the passage of time and constructed calendars to keep track of it. Our current understanding of time was established by these early timekeeping techniques, which were based on natural events. But time is more than just a means of measurement and organization. It is also a major topic in science and philosophy, raising important issues regarding the nature of reality. Is time a concept that exists only in our imaginations, or is it a genuine, physical thing? Scientists have created hypotheses to explain the role of time in the universe, while philosophers have been debating similar issues for centuries. Albert Einstein's theory of relativity was one of the most important scientific breakthroughs in our knowledge of time. According to Einstein, time is a relative concept that varies based on variables like gravity and speed rather than being an absolute, fixed reality. Because it contradicted the conventional Newtonian theory that time was an immutable, constant background against which events took place, this concept was revolutionary. The idea of spacetime, a four-dimensional continuum that combines the three dimensions of space with the dimension of time, was first proposed by Einstein's theory. According to this concept, space and time are inextricably linked. The universe's events take place in both space and time, and the presence of mass and energy affects the curvature of spacetime. This implies that depending on the gravitational field, time may move differently in different regions of the universe. Time dilation is among relativity's most well-known consequences. This phenomena happens when an object is in a strong gravitational field or moves at a large fraction of the speed of light. Relativity states that an observer in a different frame of reference will see time as moving more slowly than an object in motion or in the gravitational field. The behavior of clocks on satellites and airplanes, as well as measurements of particles traveling at high speeds, have experimentally verified this. It is both intriguing and confusing to consider that time can be changed or controlled. It implies that time is more complicated than our daily experiences could make us think. In our day-to-day existence, we believe that time moves consistently and unavoidably from the past into the present and then into the future. making sense of our lives, creating memories, and looking ahead are all done in this straight line. However, the underlying essence of time might not be so straightforward. Time has a different meaning in quantum physics, which deals with the laws governing particle behavior at the tiniest scales. Compared to conventional physics, the concept of time in quantum mechanics is less clear-cut and intuitive. For example, according to some interpretations of quantum mechanics, time may be reversible, which would indicate that the line separating the past from the future is not as sharp as we may believe. Philosophers and physicists have also been fascinated by the issue of time's beginning. The Big Bang Theory, which holds that the world started as a singularity around 13.8 billion years ago, is the most widely accepted scientific explanation for the universe's genesis. The idea of time as we know it might not have existed before to this incident. The Big Bang signifies the start of time itself as well as the universe. The question of what preceded the Big Bang is thus brought up. The concept of before might not even apply if time started with the Big Bang, which would call into question our basic comprehension of cause and effect. Additionally, time is closely related to our perception and consciousness. Time is subjectively perceived by humans, and this perception can change based on a variety of events. For instance, while we are enjoying an activity, time can seem to fly by, but when we are bored or nervous, it can seem to drag on. In an effort to comprehend how the brain interprets and processes time, psychologists and neuroscientists have investigated this subjective perception of time. Our perception of time is significantly influenced by memory. Imagination and prediction are the foundations of our ability to project into the future, while memories form our perception of the past. Our understanding of time would be very different if we didn't have memory. Time is frequently perceived as a continuous narrative, a story we tell ourselves about our life, and it is influenced by our memories and expectations of the past. Let's now discuss the relationship between time and the universe's origin. The Big Bang, which signifies the start of the universe as we know it, is closely related to time. According to the Big Bang Theory, the universe began around 13.8 billion years ago at a singularity, a very hot and dense point. This incident did not only result in time itself was born at the same time as the universe. The idea of time as we know it may not have existed prior to the Big Bang. Since time is the foundation of our entire existence, this is a difficult concept to understand. Our world has a past, present, and future, and things happen in a certain order. But when we discuss the cosmos before to the Big Bang, we are addressing a domain that is outside the bounds of time as we typically understand it. To visualize this, think of time as a thread that runs through the universe. That thread starts at the very beginning with the Big Bang. Since the thread of time did not yet exist, there is no before in the conventional sense. It is impossible to use what we now know about science to describe a time before the Big Bang because the singularity is where the laws of physics as we know them break down. The singularity, the point at which the known rules of physics stop working, would be encountered if we could, in theory, travel back in time to the very beginning. The singularity is a threshold that is outside the realm of our present comprehension. It's like running against a wall in our understanding, when space and time are so compacted and entangled that they can't be distinguished. The curvature of spacetime becomes infinite at the singularity, indicating that time as we know it could not exist in the normal sense due to the immense gravitational pull. This is one of the reasons it's so hard to talk about time before the Big Bang. The singularity is a situation in which the typical divisions between past, present, and future become meaningless due to the distortion of spacetime itself. One of cosmology's deepest mysteries remains the topic of what occurred before the Big Bang. According to certain ideas, time may be cyclical, with the universe undergoing infinite cycles of expansion and contraction. According to this theory, the cosmos may have collapsed back into a singularity and then exploded outward once more in a new Big Bang, making the Big Bang one of many such occurrences. Time unfolded alongside space as the universe grew out of the singularity. Although this expansion is frequently compared to an explosion, it's crucial to understand that the Big Bang was an explosion of space rather than an explosion in space. What physicists refer to as spacetime is a four-dimensional fabric that includes the one dimension of time and the three dimensions of space. Inflation, the universe's rapid expansion, is linked to the beginning of time. The cosmos expanded quickly in the first fractions of a second following the Big Bang, generating enormous amounts of space and laying the groundwork for the eventual creation of galaxies, stars, and planets, as well as the formation of matter. The beginning of time as we know it also occurred during this inflationary period. The cosmos was extremely tiny, hot, and dense at the time of the Big Bang, as we can see when we travel back in time. These conditions increase in severity as we approach the Big Bang event. Retracing the universe's history from its current vast condition to the smaller, denser state that existed billions of years ago is what we mean when we talk about going back in time. It's also possible that the Big Bang marked the beginning of our specific universe rather than the beginning of everything. According to the multiverse idea, there could be innumerable more worlds besides our own, each with its own timeline and set of physical rules. In this case, our reality has time as we know it, but other universes may have different types of time or none at all. From a practical standpoint, the speed of light limits our ability to travel back in time. Because it takes time for light from far-off things to reach us, the farther we gaze into space, the farther back in time we perceive. We are essentially peering back in time to a moment when the cosmos was much younger when we study galaxies that are billions of light years away. But going back in time physically is a different matter. Time travel presents a number of paradoxes, and in physics, contradictions are a problem, yet in science fiction, they are a favorite topic. The grandfather conundrum is a well-known conundrum in which a time traveler could potentially stop their own existence by altering the past. These paradoxes draw attention to the difficulties and possible impossibilities of time travel as we currently understand it. Certain extreme circumstances, including being close to a black hole or passing through a hypothetical structure called a wormhole, may make time travel feasible, according to some physics theories. Time itself acts significantly differently in the vicinity of a black hole, which is created when a huge star collapses and produces an enormous gravitational field that distorts space-time to such an extent. According to theory, time would move far more slowly for someone orbiting near a black hole than for someone far from it. Wormholes are yet another hypothetical concept. They are thought of as space-time tunnels that would be able to link distant locations in the cosmos or even different eras. Though this is still only theoretical and faces many practical and scientific obstacles, time travel might be possible if wormholes exist and could be stabilized. Our comprehension of time as a dimension is also connected to the concept of time travel. Theoretically, we could move ahead and backward in time, just as we can move forward and backward in space. Time appears to go solely in one direction in our everyday lives, from the past to the future. This is called the arrow of time, and it has a lot to do with the idea of entropy. According to the second rule of thermodynamics, entropy, a measure of disorder, tends to rise with time in a closed system. Since we see that the universe transitions from lower entropy to greater entropy states, this provides us with a direction for the passage of time. A shattered cup, for instance, won't put itself back together on its own, since doing so would reduce entropy, which goes against how time naturally passes as we see it. According to the arrow of time, the physical processes in our universe are orientated towards the future by nature, even though we can theoretically envision traveling backward in time. Because of this, we actually perceive time as moving forward rather than backward. The Big Bang's role at the beginning of time also begs the question of what will happen to the cosmos in the end. Does time have an end if it has a beginning? A big freeze, in which the cosmos grows colder and more desolate as stars burn out and galaxies separate, is predicted by some theories to occur as the universe expands indefinitely. Time would go on forever in this scenario, but the universe would eventually come to a point when nothing important would happen. The universe may someday cease expanding and start to contract, according to other ideas, causing a big crunch, in which everything crashes back into a singularity. In such scenario, time could end the same way it started, with the Big Bang. Other theories include the Big Bounce, which postulates that time may not be linear but rather cyclical as the universe expands and contracts. Let's now talk about why time advances and whether time travel is feasible. For years, people have been fascinated by the idea of time travel, which has been the subject of several books, films, and ideas. Deep problems concerning the nature of time itself are brought up by the idea of traveling through time, either to go back in time or to jump into the future. The topic of why time only travels in one direction, often referred to as the arrow of time, is at the heart of this conversation. We all experience this one way. Flow of time. We live in the now, remember the past, and look forward to the future. However, why does time go forward rather than backward? And might it ever be feasible to go across time? Examining the idea of entropy, a fundamental concept in thermodynamics, helps explain why time appears to flow in only one direction. According to the second law of thermodynamics, entropy, a measure of disorder or randomness in a system, tends to rise with time in a closed system. We can determine the direction of time flow thanks to this increase in entropy. Let's say a cup breaks on the floor after being dropped. When the cup breaks, entropy rises and the fragments become more disorganized than they were when the cup was complete. This is an irreversible procedure. The cup won't reconstruct itself on its own under typical conditions. The arrow of time manifests itself in this irreversibility. Our perception of life is closely linked to the arrow of time. We age and accumulate memories as we go through time from the moment of our birth. The thought of time running backwards seems so weird and unnatural because our brains are programmed to process time in this linear sense. Although we think of time as being one way, this isn't always the case according to the principles of physics. Time symmetry characterizes the fundamental equations of physics, including those found in quantum mechanics and Newtonian mechanics. This implies that the laws would remain valid even if time were to be reversed in these equations. Theoretically, the procedures controlled by these equations might occur in the opposite order. However, in practice, we don't witness time reversal in our daily lives. This leads to the fascinating subject of time travel. Is time travel feasible if the laws of physics are time symmetric? Is it possible for humans to travel through time in the same way that we travel through space? Scientists and intellectuals have investigated the possibility of time travel, and physicist Brian Cox is among the most well-known modern commentators on the subject. Time travel has come up in a number of presentations and interviews by Brian Cox, who is renowned for his ability to communicate difficult scientific concepts in an understandable manner. Cox claims that because of the effects of relativity, time travel into the future is not just a theoretical possibility but has already been observed. Time is relative, according to Einstein's theory of relativity, especially special relativity. Depending on your pace and the strength of the gravitational field you are in, it may pass at varying speeds. For example, compared to someone who stays still, time would slow down for you if you were traveling near the speed of light. Time dilation is the term for this effect, which has been verified by experimentation. Time moves a little more slowly for astronauts on board the International Space Station than for humans on Earth because of the station's rapid orbit around the planet. This means that even if the difference is only a few fractions of a second, they are, in theory, moving quicker into the future than those of us on Earth. Therefore, it is feasible to travel into the future in time. However, it is not the type of time travel that is frequently envisioned in popular culture. You cannot simply enter a machine and be decades ahead of time. In contrast to the rest of the world, it is about experiencing time more slowly. The effect gets more noticeable the faster you move. However, we now lack the technological capacity to achieve speeds that are even near to the speed of light. This is where time travel becomes considerably more difficult. Time dilation and forward time travel are made possible by special relativity, but going back in time presents a number of problems and conflicts. The grandfather paradox is one of the most well-known of these, in which a time traveler could be able to stop their own creation by influencing past events, such preventing their grandfather from meeting their grandmother. The concept of reverse time travel and its accompanying paradoxes have been discussed by Brian Cox. Although the concept is intriguing, he says it might not be feasible as we think. According to Cox, Time loops that allow one to go back in time are theoretically possible in some solutions to Einstein's equations, such as those involving closed time-like curves. These solutions, however, frequently call for substances or circumstances that are not present in our universe, such as unusual types of matter with negative energy densities. Furthermore, the structure of the cosmos and the principles of quantum mechanics appear to preclude the feasibility of backward time travel because doing so might result in causal paradoxes that would undermine the coherence of reality. Cox also emphasizes how entropy keeps time travel from happening in the past. Moving backward in time would suggest a decrease in entropy, which is contrary to the second law of thermodynamics because entropy tends to rise throughout time. This means that, given what we currently know about physics, backward time travel is not only improbable but maybe impossible. Thank you for seeing this video. Please give it a thumbs up and subscribe for more if you thought it was informative.